Hi everyone, today we're going to be looking at something called resultant forces. So if you can, make sure that you've got a piece of paper or your exercise book, a pen, maybe a pencil, a ruler, and a quiet place to work. Sort those bits out, get the date and title written down, and then press play when you're ready to continue. So as I said, today we're looking at resultant forces. We're going to talk about what a resultant force is. We're going to look at some things called vector and scalar as a bit of an introduction, and there will be some calculations. Now there's simple calculations today, but you might want a calculator just to make it a bit easier. So to start off with, I've got here a picture of a plane. Now this is something called a free body force diagram. So that is a free body diagram. Apologies, that's a poor writing today, but we'll cope with that. So free body diagrams. Now they show the body, which in this case is a plane, just one object with forces acting on it. So to start off with, what I'd like you to do is to draw that plane, or just write the word plane, add the 4 arrows, and see if you are able to draw or write what the name of the force is that goes around each of those arrows. Now also, I've got here a person pulling a box, and that has 4 arrows on it as well. So pausing the video, label each of those arrows, and I will go over the answers when you press play. So answers for this then. On the plane here, we have acting downwards the weight. Now remember, that is the effect of gravity on the mass of the plane, pulling that plane down. So it's a downwards force. Acting opposite to that, we have lift. Now, if the plane is travelling at a constant height and not going up and not going down, then those two forces will be balanced, and we're going to be looking at that today. The other two forces on the plane, forwards, we have thrust, and that is the force of the engine pushing the plane forward. But as we've talked about last lesson, all forces have an equal and opposite reaction. If something's moving at a constant speed or is at rest, and if this plane is going at a constant speed, the same size in the backwards direction, we have drag. Now drag is a type of friction. We could call this air resistance. Drag can also be water resistance, but we'll just call it drag here. So we have 4 forces acting on this plane. At the minute, the arrows are all the same size. That's very important, and it's something we're going to talk about today. On the man with the box, again we have weight going downwards. Now we're only looking at the box here. There would also be weight acting downwards from the man, or the woman, could be in trousers, but we're just going to look at the box. So weight pushing downwards. Now acting in the opposite direction to weight is not lift, it's not up thrust. This is called the normal reaction force. Now this is just the force that acts on the ground, well, with the ground pushing back on the box. So weight pushes downwards from the box to the ground, and because the box is not moving up or down, there has to be an equal and opposite force. So we have the normal reaction force pushing up, that's the force of the ground pushing up on the box. Then we have friction acting backwards. As this person pulls the box, the 2 surfaces rub together just here, and so you will get friction anytime 2 surfaces rub together. And then this one here, the force in the rope as the person pulls it, that is known as tension. So that is the force that keeps that rope tight as he pulls it. If you didn't get those right, just make sure you've got the correct names written down on your diagram. If you need to, pause the video and get those written down. So what we have seen just there is that forces always act in a direction, and that's really important to be aware of. Now because forces are a quantity, something that has a size that has to act in a direction, we can call this a vector quantity. Now this is a key term that we are going to talk about more as we go through this topic, but vector quantity is quite important. So the word quantity means that there is a size associated to it, and vector means direction. So direction for vector, and size just means, or quantity just means size. So looking at our diagram again, what we can see is that the weight is acting downwards. The weight of the plane can't act up, it's weight due to gravity, so it has to act downwards. The engine pushes the plane forwards, so thrust acts in that direction. The direction is associated to the thrust. Lift keeps it up in the air, that's why that is going upwards, and drag always acts in the opposite direction to the thrust, so drag will always be going in the opposite direction to the movement of the vehicle. So forces always have directions associated with them, and that's why we use arrows. So let's have a look at vectors in more detail. So on the previous slide, we said that vectors are quantities or measurements, something that has a size, that also have a direction associated with them. So we would say weight 10 newtons down, lift 10 newtons up. We would always say the size and the direction of the force. Now we have the opposite. Quantities or measurements that don't have a direction are called scalar quantities. So you can pause the video and write those down. And I have a little task for you now. I'd like you to decide if each of the following quantities or measurements are vector or scalar. So that means, do they have direction associated with them? So if you're measuring them, do they need a direction or no direction? And the words we have are length, velocity, area, mass, temperature, displacement, weight, friction, density and speed. Now if you're not sure about any of them, just have a guess. I would suggest that you either write out the words and then put V or S next to them, or possibly you might want to draw a table with vector in one column and scalar in the other. Up to you how you do this. Pause the video and press play for the answers. So I'm going to put my answers here as a table, vector and scalar. Now remember that vector are the things that have direction and scalar are the things that do not have direction. They're just measurements. So the vectors are displacement, weight, friction and velocity. Now anything that is a force is always a vector. So any of those force keywords that we've looked at already will always be vectors. And everything else in the list is scalar, and that just means we can measure it and the direction of the measurement doesn't matter, it's just a quantity that we're measuring. So length. The length of a pencil doesn't matter if the pencil is lying flat or standing on its end, the length of the pencil remains the same. So anytime you measure the length of something, that's always a scalar quantity. The same goes for speed, area, mass, temperature and density. They're all just quantities and direction doesn't matter. Now we're going to be looking at some of these in a bit more detail later on in the topic. So displacement and distance or length go together, and velocity and speed, you might think of the same thing, but velocity always has to have a direction. If you're not sure about any of those, don't worry about it for now. Just make sure you've got the right answers written down, pause if you need to, and press play when you're ready to carry on. So just to have a look at this in a little bit more detail, we're going to compare displacement and distance. Now distance and length are kind of very similar, so we could use both of those. So displacement is a vector quantity and distance is scalar. Vector means that it has direction and distance means it doesn't. So I've got here an example question. A taxi driver drives 4 kilometres north and then turns due east and travels for another 3 kilometres. We can see his journey here. Taxi driver starts at X, travels north for 4 kilometres and then turns due east or right and goes 3 kilometres. If the question says what is the distance travelled, then that's literally how far he has travelled. What is the distance that taxi driver has driven? And if we were to look at this, it would need to be the total distance that he's travelled. So 4 kilometres north, then 3 kilometres. So the distance travelled would be a total of 7 kilometres. And it doesn't matter that he went north and then turned east. He could have gone north, then turned round or reversed and gone back 3 kilometres to where he started. He's travelled 7 kilometres in terms of his distance. Now, the displacement of the taxi, displacement is a vector, and displacement here would actually be how far he has moved, not how far he's travelled. Now this is supposed to be a straight line, so just pretend I've drawn a straight line with a ruler there. So the taxi driver has displaced or been moved from X to Y. And if we were to work that out, we would need to use a little bit of Pythagoras theorem there, which we're not going to worry about today. And I've got that wrong there, so just change that back. So what the taxi driver has done is actually moved 5 kilometres in this diagonal direction. Now we could actually work out the angle that he's travelled here, but we'll say approximately northeast. So the displacement is 5 kilometres northeast. He has been displaced, moved from X to Y. It's not the distance he's travelled, it's just how far he's been moved from start to finish. Now, as I said, that's a little bit complicated to get your head around. We're going to come back to that in a later lesson. So really don't worry if that has gone over your head right now. We will come back to it in a later lesson when we're looking at motion calculations. So, to relate to what we've been talking about with forces, we're going to be looking at balanced and unbalanced forces. And as I said, we're going to talk about the resultant forces. So, compare the two pictures of a tug and war competition. We've got the top picture and the bottom picture. Sketch the pictures in your notes, and you can use stick men. Don't spend a long time drawing this. We just need to know that there's 2 men on the left, 4 men on the right on the top picture, and then an equal number of people on the bottom. And then number 2, I'd like you to describe what will happen in each of these pictures using your knowledge of forces. Now we have to assume here that all of the people doing the tug of war have equal strength and they're going to pull with an equal amount of force. But see if you can describe what will happen. Now remember, describing is just saying what will happen. We don't need to give reasons why necessarily. But pause the video and see what you can come up with. So, in this diagram, we've got 2 men on the left-hand side and 4 on the right. So what's going to happen here is that there is a bigger force pushing to the right or pulling to the right-hand side. So the force is going to be greater, and what will happen is that these 2 guys on the left-hand side will be pulled to the right. They'll be pulled in that direction, might even fall over. Now they'll actually be accelerating to the right. They'll start off not moving, and if they're not moving to begin with and then they move, they have to be accelerating or speeding up. Now at the bottom, both of these will be pulling with an equal amount of force. So we'll be having the guys on the left pulling to the left and the guys to the right pulling to the right. And that means that they cancel out. The forces are in opposite directions, they will cancel, equal and opposite forces, which means that they won't move anywhere. They'll just stand there pulling on the rope and not move. So to look at this in a bit more detail, if we were in the lab, we could actually try this out. We've got 2 Newton meters here. Now Newton meters measure force, spelt with an ER because it's a measuring device as opposed to RE for the measurement meters. Now each of these Newton meters are the same. Okay, we have to assume that they are identical, and so what we've got inside is in the middle here there is a spring, and then there is just a scale here, and as you pull the spring with a certain amount of force, it moves down and tells you how much force you're using. So it's a very simple device, a Newton meter. Now, if we link them together as they are in the middle and pull equally hard from both ends, the forces recorded on both will be the same. So if we pulled with a force of 10 newtons on the left and 10 newtons on the right, then they would read 10 and 10. And overall, those hooks in the middle, the Newton meters, wouldn't go anywhere because the forces are balanced. That's because the forces acting on these central hooks will cancel each other out. They're equal in magnitude, which is a fancy way of saying size, and they're opposite in direction, one to the left and one to the right. Now, because the forces are balanced and the hooks weren't moving to begin with, the hooks won't move. Remember, balanced forces mean that things either stay still or continue moving at the same speed. And because these were still to begin with, they will stay still or at rest. Now, if we were to look at unbalanced forces, what would happen if the pull on one end is greater than the pull on the other? For example, if the left-hand Newton meter was pulled with a force of 15 newtons, but the right only pulled with a force of 10, what would happen to these hooks in the middle? Well, in this case, the forces acting on the hooks are no longer balanced. Both hooks will start to move to the left. Their speed will change. And as I said already in the video, this is called acceleration. The hooks were at rest or still at the beginning, and because they start to move to the left, that means that they are speeding up, they accelerate. So we've got here an overall force going to the left-hand side, causing movement that way. And that's what the resultant force is, the leftover force after you've cancelled the 10 on the right out with some of them on the left. Now, something that's really important that we've said already is this sentence at the bottom. Unbalanced forces lead to a change in speed or direction. Now, I think that's really important for you to write down. So if you're only making brief notes, make sure that you have got that sentence at the bottom written down. So maybe pause the video. So I've got here a little bit of a copy and complete, which I'd like you to do. So you're going to pause the video, copy and complete this slide, and you've got to try and work out what goes in the gaps. If you are a bit stuck, then there will be some words coming up in a word bank at the bottom, and you will need to use each word once. But I'd like you to pause the video just to begin with and have a go without the words, but press play if you do need them. Okay, so if you do need some help, the words that you need are constant, speed, accelerating, change, and remain. Okay, let's have a look at the answers then. So, forces come in pairs. Balanced forces produce no change in movement. If at rest, then an object will remain at rest. If already moving, then it will move with constant speed. Unbalanced forces change the speed or direction of an object. Changing speed means you are either accelerating or decelerating. So if you weren't quite right with those, just make sure that you've corrected your answers. You must make sure that if you got it wrong, that you've corrected it and put the right word in the right place. Pause the video if you need to do that now. So to have a look at force diagrams, which I've already mentioned already, we're just going to have a look at a bit more detail and explain some really important things about these diagrams. So as I've said already, these diagrams show each force acting on an object using an arrow. Now only the object is shown. At the beginning we looked at the plane in the air, nothing around it. We looked at the box on the floor, no ground was shown, so no surroundings are shown. So here I've got two people doing a tug of war again. They start off still, they're not moving, and they're just pulling on that rope. Now when it comes to the arrows, the length of the arrow shows the size of the force, not the width. So it doesn't matter how fat the arrow is, that has no bearing on the size of the force at all. It is the length that is important. So here I've got two arrows and they are the same length, they're just acting in opposite directions. So the blue arrow is for this guy on the right hand side who's pulling to the right hand side, and then we have this person on the left, they are pulling to the left with the red arrow. Now these are both the same size, I can guarantee that. I copied and pasted them and just flipped one. So we've got these equal forces. And as the arrows are the same length, the people don't move. If they weren't moving at the beginning, they won't move when they start pulling with equal force. What would happen if we changed the number of people? Think back to what we said earlier. Now, if I add 2 extra people on the left-hand side, the group is going to accelerate left as the force is greater. This is due to a resultant force. So what we've got here is this blue arrow in the right direction, in that way. Now, that blue arrow is going to cancel out the same amount of force that's acting in the left-hand direction. So this bit of force that we've got here will have no effect. However, this force here on the left-hand side is sort of extra. That's an extra amount of force that the people on the left are exerting on that rope or pulling on the rope with. And that's the size of the force that causes the acceleration to the left-hand side. So the resultant force is that sort of over or leftover force after the other forces acting in the opposite directions have cancelled out. Now, to look at that in a bit more detail, I've got this diagram here showing 2 people pulling a piano. We've got one guy on the right hand side pulling the piano with 150 newtons of force, and then the guy on the left is pushing with 100 newtons of force. Now the total amount of force here will be the 2 forces added together, 100 newtons plus 150 newtons, because they're both in the same direction, and therefore the resultant will be 250 newtons. The total overall force will be 250 newtons to the right. So the piano accelerates right with a force of 250 newtons. These forces are in the same direction, so the resultant force is the total of the forces added together. Now I'd recommend that you pause the video here and that you jot that down. Maybe write the word piano, draw some stick men, but make sure you've got the arrows with their size. Now to look at a second example, here we have the 2 people with the piano, and this time one is pulling to the right with 150 newtons again, but this time this guy here is pushing in the opposite direction. Now that's obviously going to make the job a lot harder for the orange guy. Now if we think about the size of the overall force, these forces are in opposite directions. So we take the smaller force away from the larger force. Now the direction will be the same direction as the larger force. Now to look at that with the arrows, we've got 150 newtons in the right and only 100 newtons in the left hand side. So the 100 newtons that the guy drawn in black is pushing on the piano with is going to cancel out 100 newtons of the force that this orange guy is using. And overall, the resultant will be 50 newtons to the right. Now these arrows are not really to scale. Remember that this one is a third of the size, so actually should be a third of the length. So we just need to bear that in mind, that these diagrams are not very good, but in terms of the numbers they work. So the overall resultant force is that the piano accelerates right with a force of 50 newtons. Now remember, it's a vector, so the fact that it's going to the right hand side is very important. So accelerates right with a force of 50 newtons is us describing the resultant force of this diagram. So to finish off, I've got here a little exercise for you to do. I would like you to, as it says, draw and calculate the resultant force for each force pair. So in each case, in each of these 4 cases, we've got these arrows. Draw them in your book, try and keep them to scale. So if one's longer than the other, make sure it is longer than the other, and make sure they're labelled. It is really important to show your working. So I want to see these copied and then calculated, please. Pause the video and then press play when you're ready for the answers. Mark your own work. Okay, so let's go through the answers here. So for number 1, we have 8 newtons acting left and we have 8 newtons acting right. The forces are opposite each other. So because they're opposite each other, what we're going to be doing is taking them away. So 8 minus 8 newtons equals 0 newtons. There is no resultant force. Okay, so what we've got here is that they'll be balanced and it won't move anywhere, it won't accelerate, it will stay still if it's already still. For number 2, we have 12 newtons left and we have 8 newtons right. Now because they're acting in opposite directions, we take them from each other. So the resultant force will be 12 newtons minus 8 newtons. So the size will be 4 newtons. And because it's a vector, we have to give direction. And the 4 newtons is acting left. And that's because this bigger force here is to the left-hand side. So the overall force will be 4 newtons to the left. Now for number 3, we have 5 newtons to the right and we have 8 newtons to the left. Now again, they are in opposite directions, and if they're opposite, we take them away from each other. So the 8 newtons take away the 5 newtons, because it's always bigger minus smaller. We have an overall resultant of 3 newtons, because the 5 will cancel out 5 from the 8. And the direction, again, is going to be left, because that's the direction that the bigger force is pointing. So this will be 3 newtons to the left. And then number 4, both of our arrows are pointing in the same direction. So if they're pointing in the same direction, they get added together. So 8 newtons plus 5 newtons totals 13 newtons. And both of these arrows are going to the right hand side, so the resultant force will be 13 newtons to the right. If you have any questions about any of that, please send me a message and let me know. I'll do all that I can to help you.